Hi there, welcome back to another lesson of Assembly 6502 on the Apple IIe. So today we take a look into animating with the high resolution graphics mode. Before we actually get into assembly, I want to show an example using AppleSoft Basic. This example, let me run it first before I explain what it does. So you might be able to see it's kind of flickering, that there is a dot that is moving around the high resolution screen. I'll try to show you. It's here, it's there. So this dot is basically moving around the screen, and every time it hits one of the corners of the screen, it bounces. So the way this works is we get into high resolution graphics mode, and then we have an XY position, that's the initial coordinate at the center of the screen. And then we have an X and Y offset that we'll use to calculate the movement. So we start by drawing the dot on the center position, and then we erase it and calculate the new position. So we calculate an offset. As I mentioned, it is sort of bouncing, so it's going on diagonal until it hits one of the corners of the screen. One of the boundaries of the screen, right? Imagine the screen as a rectangle. Every time it hits one of the edges, it flips the diagonal either vertically or horizontally to move like if it were bouncing. So we draw the dot, we erase the dot, we calculate the next position, and then we repeat. So the reason why this sucks and you can barely see the dot, it's because Basic is sort of slow, right? So the time it takes to make the calculation of the next position takes long, and then the animation is very glitchy. So let me put another version of the Basic program that makes this better. Okay, so I have pasted here a new version of the Basic program. Let's update it in memory and run it. There we go. So this version has a few improvements. So the first one is we are drawing the boundary of the screen, this line here. We basically draw a rectangle around the screen. And then we are first calculating the new position, and then we are erasing the old position and drawing the new one. So by doing that, we ensure that the calculation is not sitting between the erase and the plot, causing all that glitch. But you see, the dot is still kind of moving quite slow. It's limited. This is sort of as fast as it can go using Basic. And also it looks a bit glitchy, right? It looks like it's a duplicated dot. So next step is to do the same thing in assembly. And you can see here the assembly program. I will assemble it. I'm gonna show you the execution, and then we understand better how it works. Oh, this is how I would do it with Basic, right? So let's call the assembly routine. So first thing I hope you notice, the dot is moving way faster, and it actually changes speed as I move the pedal. If I move it here, it's slow. If I move here, it's super fast. And I'm gonna explain the code so we understand why is it so. Let's then take a look at the code listing on the assembly lines book. We start setting the program at the usual location. And then here you can recognize basically the variables that we use to indicate the X and Y coordinate, and temporary variables to calculate the displacement. And here we have a number of subroutines from the monitor that we use to set a high resolution graph color, set graphics mode, hplot, and it's an interesting new one, the wait subroutine. Basically, it's going to wait for a number of milliseconds that are specified on the accumulator. So we start our program by painting the box, right? Painting the frame around the screen using H-plots. Then we set the original values of xv and yv, the displacement variables, plus the x and y coordinate to be at the center of the screen. And then we add the x to xv and y to yv. That gives us the actual coordinate to be plotted. And then we check whether that is still within the boundaries of that box. And if it's not on the box, then we revert the numbers of tx and ty to make it basically bounce and change course. So all these checks, check 1, check 2, 3, and 4, basically check for the frames, the different edges of the screen. And you see that in some cases you say like reverse y or reverse x, and there's routines that do these things, and they have to deal with negative numbers. So we haven't seen negative numbers so far. But the idea is when you are dealing with negative numbers, you're using a certain bit to indicate the sign, whether it's positive or negative. And the way that you convert a number that's positive to negative, let's say you want to go from positive 52 to negative 52, what you do is you reverse each one of the bits. So if it's a 0 becomes a 1, if it's a 1 becomes a 0, and you add 1, because that's going to flip the right bit for the positive or negative. So you do that basically by doing an exclusive OR. So the exclusive OR is forcing each bit to become its inverse, and here we just add 1. So this is how you convert positive to negative, and converting negative to positive is the other way around. So you subtract 1 and then you use the exclusive OR logical bitwise operator to reverse all the bits. Actually, I said operator, I mean the opcode, the instruction. And you're gonna see this when we have this reverse x, reverse y. There's this basically this thing is going on, that we are ORing certain numbers and adding 1. Like here, we basically starting with $FF and then making it negative. And the only other remarkable thing here is that once we check and we change the directions, and then we erase the point, we plot the new point, right? We erase the old one, then we plot the new one, and then we wait a certain delay. And this delay is calling the wait subroutine, as we discussed. But not only that, it's also loading the accumulator with what it reads from the pedal. So if the pedal, as we saw, it's a predecessor of the joystick, and in our environment we don't have physical pedals, but we use the mouse. So depending on the position of the mouse on the screen, you have a different value for that's being read here and put in the accumulator. So the more you go to the right of the screen, the larger the weight value becomes, and that's why the dot was slowing down as we moved the mouse around. And basically we jump back to the calculation and we calculate the new position, and we keep doing that. So you can see the result was much faster than basic, right? Assembly it just performs much faster, and you can accomplish superior quality of animation. That's why everything that was really dealing with sophisticated graphics, at least for what was sophisticated in the early 80s, everything that had to do with sophisticated graphic effects on the Apple II was made via assembly at some point. And that wraps our lesson of today, and hope to see you next time.